3.3, Logarithmic Functions. So in 3.1, we talked about inverse functions. In 3.2, we talked about exponential functions. So combining together those two ideas, we should ask ourselves, what is the inverse of an exponential function? What is the inverse of the exponential function y equals b to the x? I know we used a as the base, but let's use b as the base for now, for reasons. So what is the inverse of the exponential function y equals b to the x? And the answer is logarithms. The story of today is all logarithms, and logarithms are the inverse function to exponential functions. So, hold on a sec. So, if we have y equals b to the x, the equivalent statement using logarithms would be log base b of y is equal to x. It looks weird. We're going to talk about it. First of all, we're going to talk about saying it out loud. So this is log base b of y is x. Okay. So logarithms are special in that there's a little number written down here and it's with a subscript. So this is not in line with log. It's a subscript down here, and this is the base of the logarithm. So this guy right here, b is equal to the base of the logarithm. The exponent becomes the output of a logarithm. So the exponent of an exponential is the output of a logarithm. Logs output exponents. And then the inside part, so the inside of the log, the input to the log, is the answer from the original. So the answer from the exponential expression or equation. So one of the skills that we're going to need to talk about right away is the ability to switch back and forth relatively quickly between exponential form, so this guy right here, y equals b to the x, this is exponential form. And log base b of y equals x, this is logarithmic form. These two statements are really saying the same thing, but they're saying the same thing in different ways. So these two are inverses of each other. Logs are inverses of exponential functions. Exponential functions are inverses of logarithmic functions. And we've talked about what the properties of inverses are, but I'm going to kind of make them crystal clear right now of how they relate to exponentials and logarithms. So we're going to first talk about the inverse relationship they have, and then we're going to talk about how to make the switch between the two of them fast. So a quick recap on inverses. We said that two functions were inverses, and we use this little notation with a -1 up there to say inverse. So this is f inverse of f of x is equal to x. Remember, if you composed the two, that they just kind of cancel, and the order didn't matter. So f of f inverse of x would also come out to be x. Right? That was what was required to be an inverse. So I am claiming to you that if you have the function f of x equals b raised to the x, I'm claiming that the inverse function is log base b of x. I can't really prove this to you. This is just a fact you're going to accept because this is just the definition of what a logarithm is. But it brings up, you know, some fun stuff. Let's do some compositions and see what it looks like. So we'll start with f inverse of f of x. So f of x is b raised to the x. So f inverse of b raised to the x. F inverse is log base b of x. We're just going to replace the x with b to the x. And by definition, because I'm telling you that these are inverses, this has to be equal to x. So, big important thing I'm saying right now, log base b of b to the x is equal to x. The other direction, so putting the inverse on the inside. So the inverse function is log base b of x. Now we're plugging in for x. We're plugging log base b of x in for x on that exponential. So this would be b raised to the log base b of x. Yes, this looks weird because it's in the exponent, there's a subscript, so it's a little bit weird, but log base b raised to the log base b of x is equal to x. I am claiming that these two statements are true, necessary, and important. Right, because logs are an inverse of exponents. These two facts are true. The log base b of b cancels itself out, and you're just left with this x here. And down here, it's like the b and the log base b cancel themselves out again, and you're left with the x. Right. We'll get more into this. We'll hit heavier on this later, but I wanted to start with hitting a little bit on that now. So let's go back to that idea of how in the world do you rewrite these things? How do you go from one form to the other? How do I go from exponential form to logarithmic form? How do I go from logarithmic to exponential? Is it going to be a really tedious, terrible memorization process, or is there a trick? Answer, there's a trick. So let's talk about that trick. So I'm starting with y equals b to the x. I've already told you the way that this is rewritten is log base b of y is equal to x. Important thing. This method is called, I don't know, loop-de-loo method. It doesn't have a name. We're calling it a loop-de-loo method. It's important when you're doing this, we're always going to start at the base. Always start at base. Right. You start with the base, across the equals, back again, is the thing I'm going to say on repeat many times in this video. Right, this statement right here is everything you need to know about going both directions. So if I'm starting with this exponential form, and I want to write it in logarithmic form, I start at the base. So the base on an exponent is the number that has the exponent on it, and the base on a logarithm is the little subscript down here. So if I'm starting with y equals b to the x and I'm switching it into logarithmic form, I would tell myself, okay, so I'm going to write log and then base b. Start at the base, then you go across the equals. So log base b of y. And we can put parentheses. So parentheses, optional sometimes, not always optional. In the case where you just have a y on the inside, you can leave them off. But I'm going to put them there, just make them a little fancy. So start at the base, across the equals, and then back again to grab the last part, so equals x. It works the same way over here. So if I'm trying to take log base b of y equals x and switch it into exponential form, so right now it's in logarithmic form. If I'm trying to change it into exponential form, I know that it's going to be something where there's a number, an exponent equals something else, right? And we know that this guy right here is the base. So when I start at the base here, I know that that's what number goes here. So start at the base. Let's see. Okay, there we go. Start at the base. Across the equals. So that goes here, x goes here, and then back again. So you get b to the x equals y. Okay, let's do several examples. All right, let's change some logarithmic equations into exponential equations. So we're going to use this loop-de-loop trick. So here, remember exponential form, the base is here, right? This is base. This is an exponent, and it equals an answer. Right. Start at the base, across the equals, back again. So here we're starting with the m, which means this should be m, and then the next thing we're going to write is the exponent. So m across the equals, 7. So that's the exponent. And then back again. So you put an equals, and now we're doing the answer part. Back again for the 5. So m to the 7 equals 5 is the same statement, but in exponential form. Here we start with the c. So it doesn't matter what side you're on. Sometimes people start to think, oh, I'm going to always start with whatever number's on the left or whatever number's on the right, and it doesn't matter what side it's on. You always are starting with the base. So c is the base. Okay, start at the base, across the equals, so the exponent is 8, and then back again equals 6. C to the 8 equals 6. Same thing here. Start at the base, so the base is 4, across the equals, so -3 is the exponent, and back again. It's 1 over 64. So 4 to the -3 is 1 over 64. This is actually one you could check on your calculator. All right, for the last one, start at the base. The base is 12. Across the equals, we have a w for the exponent. And back again is equal to t. So 12w is equal to t. So hopefully that trick makes sense. It's real nice to use. It's not that hard once you kind of get the hang of it. So this was going from logarithmic form into exponential form. Now let's do an example where we go from exponential form into logarithmic form. It's not going to be any harder than this. So here we go, change into exponential form. So the base, remember, is the thing that has the exponent on it. So you're always starting with the base. So the base here is 1.4. So log, and then the base goes down here of log base 1.4 across the equals of r back again is equal to 5. Start at the base, that's 2, so log base 2 across the equals of 8 back again is equal to d. Okay, so both versions have 3 numbers involved, right? So with exponential form, right, base, exponent, answer. With logarithmic form, it's log, the base goes here, the answer part goes here, and the exponent is the output. But they both have 3 numbers, so it's just a rearrangement of the 3 numbers. This last problem is actually kind of special. So the base is e, and hopefully you've watched the exponential function video, and the very end we talked about the number e. It's an irrational number, yada, yada, yada. If you haven't seen it, you should go and watch that. That's part of your responsibilities as a student. But start at the base, so log base e across the equals x, and then back again is equal to y. Now, what's special about this is that we never actually write log base e. So this is a special logarithm. It's called a natural logarithm, and it has a special form. So if you watched the end of my exponential functions video, I had a screenshot of the Casio calculator, and there was a button and it said ln, and on top of it was where the e to the blah button was. So you had to push shift and then the ln button to get to the e. Well, here's where that ln button comes in. So we never really write log base e of x. Instead, we write this as ln x. So we don't write it with a base at all, we just write ln x. So the way that you say this out loud, this is L, right, the letter L, and then N, the letter N, of x. So some people say ln, I don't know, some people try to pronounce this as a word. It's not, it's ln of x. So you just pronounce each letter ln of x. So you're never really writing at log base e. That's really awkward. People will laugh at you. I'll laugh at you. I'm just kidding. I'll just scold you. You should always be writing ln x if the base on your logarithm is e. So yes, your calculator has a button for logarithms, and you could plug log base 4 of 64 into your calculator because your Casio calculator is very powerful and you could get an answer. But I want to talk about finding the exact value of these without using a calculator, because there's going to be times where this is a necessary skill in the upcoming sections. So let's say we have no calculator because we are in the wilderness and a math wizard has approached us and we need to come up with an answer to his riddle, which is, what is the exact value of log base 4 of 64? We're not panicked at all. So here's how you deal with it. Log base 4 of 64. Human brains don't appreciate logs. We don't like thinking in logs. We like thinking in exponentials. So what can we do? We can change this into an exponential. This isn't actually an exponential equation though. So to kind of remedy that, I'm just going to set this equal to y, right? We're trying to solve for whatever y is. That's what we're interested in. And then we'll do our loop-de-loo and switch it into exponential form. So start at the base, 4, raised to the, so across the equals, raised to the y is equal to 64. So what number do we need to raise 4 to in order to get 64? You could start guessing. So 4 to the 1 is just 4, right? 4 squared is 16. 4 cubed, that's 16 times 4, right? That's going to be 64. I'll just tell you, it's 64. So 4 cubed is 64. So if 4 cubed is 64, 4 to the y is 64, that means that y has to be equal to 3. So y equals 3 isn't really what we're answering. We're saying log base 4 of 64 is equal to 3. 3 is the answer there. Let's look at this one. log of 1 over 10,000. And you might say, hey, what gives? Where's the base? There's supposed to be a base right here. I could keep drawing circles forever. There's no base. If there's no base given, it is assumed to be base 10. So the base is assumed to be 10. So the two special logs we've talked about. So the first one, log of x is the same as log base 10 of x. The other one we talked about was e. Ln of x is the same as log base e of x. So if there's no base given, it is base 10. If it's ln x, then the base is e. So we're going to use the same trick that we did last time. I'm going to go ahead and write a 10 in here. And then 1 over 10,000 is equal to y. Start at the base, across the equals, back again. 10 raised to the y is equal to 1 over 10,000. Something you should know, powers of 10, positive powers of 10, whatever this exponent is how many zeros it has. So 10 to the 5th is a 1 and then 5 zeros. Right, so 10 to the 5th is 1 and 5 zeros. When it comes to negative exponents, so 10 to the negative 2, it's just a 1 in the numerator and then same rule, whatever the number is, take its absolute value. That's how many zeros on it. So 10 squared has 1 and 2 zeros. So that'd be 1 over 100. 10 to the negative 3 would be 1 over 1,000, so on and so forth. 10 to the negative 4 in particular is interesting because it's 1 over 10,000. So 10 to the negative 4 is equal to 1 over 10,000, which means that y is equal to negative 4. So log of 1 over 10,000 is equal to negative 4. Bam. So before I even go to the next slide, I'm going to mention that the next slide is a trick. Just going to throw it out there. Find the exact value of the logarithm, log 0. So I've already said that it's a trick, but let's just kind of go through it. There's a secret base of 10, right? So log base 10 of 0 is equal to y. Start at the base, across the equals, back again. So this is 10 raised to the y is equal to 0. Now here's what's interesting. We talked about exponential functions in the last section, and we talked about how if you had 10 to the x, it would look like this, with a horizontal asymptote at y equals 0, which means that it never touches y equals 0. The y value is never 0. There's not a single value that you could plug in for y here to make 0 come out. There's not an x value on this graph that makes the y value 0 because there's a horizontal asymptote there. This will never happen. This has no solution. So it's not possible to put a 0 on the inside of a logarithm. In fact, not only can you not put a 0, but you can't put any of these negative numbers. Any of these negative y values can't go inside. So the only numbers that can go inside of a logarithm are positive numbers, not 0, positive numbers. This is important. So let's talk graphs of both logarithms and exponentials, but mostly logarithms. Okay. So with an exponential, so with b to the x, we already know the domain and range of this guy. The domain of an exponential is -infinity to infinity, and the range was from 0 to infinity. Because logarithms are the inverse of exponentials, oops, let's draw that line a little better, we can expect the domain and range to just be flipped. So the range of the exponential is the domain of the logarithm, and the domain and the range of the domain of the exponential is the range of the logarithm. So the domain here is 0 to infinity, and the range is -infinity to +infinity. I told you earlier in the semester that there are total of three cases where three things you need to look for domain, but I told you one of them was coming up later, so that the only things you needed to worry about for domain were zeros in the denominator and negative numbers under an even root. The third thing is logarithms. Logarithms have domain restrictions because their base function requires that the input x is greater than 0, strictly greater than 0. Now, let's look at some graphs. I'm going to pause this and put some graph paper on here. All right, so I have myself some graph paper. Exponentials. They have a horizontal asymptote at y = 0. Okay. They have a y-intercept at 0, 1. And then they grow and stuff. So this is an exponential. Logarithms, on the other hand, instead of having a horizontal asymptote, they have a vertical asymptote at x = 0. Instead of having a y-intercept of 1, they have an x-intercept of 1. So their graph ends up looking a little like this. It actually grows very, very slowly. It's a very, very slow growing function. Exponentials grow very, very fast. Logarithms grow very, very slow. But you'll notice that there's no graph for any of the x values less than 0, and that's because of this domain restriction here. So logarithms have vertical asymptotes. They have domain restrictions. The inside part does need to be strictly greater than 0, and this is what the graph of a logarithm looks like. This is what the graph of an exponential looks like. They are related because they are inverses. We didn't talk too much about the graphical relations between inverses, so I'm not going to start now, but there's relationships between the graphs of inverse functions. I'll just throw it out there. All right, let's do some domain problems. So when you are tasked with finding the domain of a logarithmic function, you are setting the inside of the logarithm, so the inside part of the logarithm, greater than 0. So greater than 0. There is no underline on this. It's strictly greater than 0. So the inside of the log, greater than 0. So 6 minus x is greater than 0. Right? Subtracting the 6 on both sides. Cancel. Negative x is greater than negative 6. I will divide both sides by -1, but when I do that, because it's an inequality, I'm going to flip because I divided by a negative. So negative 6 divided by -1, oops, let me make that more pretty. That's positive 6, so we have x is less than 6. If I draw a number line out, right, 6 is here, less than 6 is this. This would be the interval -infinity to 6. And Alex and I would ask for interval notation on this, so you would need to give your answer like this. So negative infinity to 6 on that one, that's the domain of that function. But they can get a little bit more difficult. So looking at this one, find the domain of the logarithmic function log base 2 of x plus 2 over 2 minus x. Let's set this up. So take the inside, so x plus 2 over 2 minus x, and set it greater than 0. Here's where students start to go a little weird. We spent a lot of time talking about nonlinear inequalities and how whenever you have a nonlinear inequality that you need to create a number line. For whatever reason, when students get to logarithms, they start to think that nonlinear inequalities don't exist anymore and that number lines don't exist anymore. This is the same thing that you did in the nonlinear inequality section when you did, rational inequalities. You have to make a sign chart. That's what you'll have to do here. So setting x plus 2 equal to 0, you get x equal to negative 2. 2 minus x equals 0 means that 2 is equal to x. So you have x equals 2 and x equals negative 2. So negative 2, positive 2. Choose some test values. So we'll do negative 3, 0, and positive 3. Negative, and then plugging the test values in here. Negative 3 plus 2 is negative. 2 minus negative 3 will be positive. A negative over a positive is a negative. 0 plus 2 is positive. 2 minus 0 is positive. A positive over a positive is a positive. 3 plus 2 is positive. 2 minus 3 is negative. Positive over a negative is a negative. Greater than 0 is the positives. So we are looking at the interval from negative 2 to positive 2. And you don't have to worry about excluding things in the denominator. So when this had an underline underneath it, you had to be very careful because if it makes the denominator 0, then it causes issues. But because there's no underline, it's just open circles, it's parentheses, you don't have to worry about it. So domain on this guy from negative 2 to 2. Let's look at this. So find the domain of the logarithmic function y equals log of x squared minus 16. So the inside, x squared minus 16 needs to be greater than 0. I'm going to write some bad math down. I'll even write, this is bad math I'm about to write down. All right, and then I'll erase it. This is what students are tempted to do, and it is wrong. What I am about to write down is wrong. I cannot repeat that enough. So if you have x squared minus 16, students want to add the 16 to both sides, right? So you have x squared greater than 16, and then you just, square root both sides, and then you have x is greater than 4, and that's 4 to infinity, and bam, I'm done. Hello, that's the answer, which doesn't work. You can't take the square root of both sides of an inequality. It does not work, right? So if you have x squared greater than 16, and then you say x is greater than 4, well, what if x is equal to negative 5? Negative 5 squared is 25, which is certainly greater than 16, but negative 5 is not greater than 4, so there's an issue. So you can't take the square root of both sides of an inequality. We talked about that in the nonlinear inequality section. Instead, you're going to have to factor this guy. So x plus 4, x minus 4, it's a difference of squares. And then we're doing a sign chart. Can't get away from the sign charts. They are there to haunt you forever. So x equals 4 and negative 4. So negative 4, 4. Let's see, x equals negative 5, x equals 0, and x equals 5. Negative 5 plus 4 is negative. Negative 5 minus 4 is negative. Two negatives make a positive. 0 plus 4 is positive. 0 minus 4 is negative. Positive and a negative make a negative. 5 plus 4 is positive. 5 minus 4 is positive. Two positives make a positive. We are looking for the positives. So here we go. Negative infinity down here, positive infinity up there. So our domain on this function is negative infinity to negative 4, union 4 to infinity. If you had tried to do that bad math, you would have just got this part, which would not be correct. So there's that. So when you're doing these domain problems, you are taking the inside and you are setting taking the inside of a logarithm and setting it greater than 0. I want to show you one more that, while looking at Alex, it popped up, and it's a little bit more strange. So find the domain of the logarithmic function y equals ln of the square root of 2x plus 7. Now, in the next section, we're going to get some fun properties of logarithms that would allow you to like mess around with this and not have to look at it as critically, but we don't have those tricks yet, so let's just kind of look at it. The inside part of the logarithm is the square root of 2x plus 7. The square root of 2x plus 7. And if I say set it greater than 0, you'd say, well, all square roots are going to come out to be positive. Unless there's a negative in here, which is a different problem, square roots in general are positive numbers, right? If you click the square root button on your calculator and you put whatever positive number you want here, it's going to hand you a positive number. So that part's actually taken care of. But there were 3 things that we needed to check for domain issues. So the first issue, no 0 in denominator, which we don't have a denominator, so that's no big deal. So that's taken care of. Number 2 is no negatives under square root. That's what we need to be concerned about. So the square root part isn't really an issue. It's not going to cause issues for the domain, but we do need this inside part to be positive. And we don't want it to be 0, right? We don't want the square root of 0 because that would be 0 and that's not greater than 0. So what we're looking for is 2x plus 7 to be strictly greater than 0. Right? So no negatives under the square root is what we're going to take care of here, because only positive numbers inside here is basically been taken care of, minus the fact that we just need to leave off the underline here. So no 0 or negatives inside logs. So 2x plus 7 is greater than 0. Subtract the 7. 2x is greater than negative 7. X is greater than negative 7 halves. So this would be the interval negative 7 halves to infinity. So just, keep in mind all of your log rules there. Square roots themselves will only shoot out positive numbers. They can shoot out 0. That's why we were really careful and didn't put an underline there. But as long as you're not putting underlines here, you should be fine in getting your answers. So that's all I have to talk about for this section, I think. Yeah, that's all I'm going to talk about. So I will see you in the next video. Next week, we will be talking about properties of logarithms, which is honestly my favorite. There's 2 sections in 126 that are my favorite. It is the next 2 sections we're going to do, properties of logarithms and exponential and logarithmic equations. I think they're so much fun. I think you guys will enjoy it if you just let yourself be open to enjoying it. All right, I hope you have a fantastic day. I will see you in another video.